When mentioning the Himalayas, we all feel overwhelmed by the majesty of nature. Yet right here, the team of Indian engineers and workers is carrying out the construction of the Zojila Tunnel, the longest two-lane road tunnel in Asia, by digging through the roof of the world. This is Zojila Pass, one of the most dangerous passes in the world, but for decades it has remained the only transportation route serving the transport of goods, fuel, and troops from Jammu Kashmir to Ladakh. Every year, snow covers it for up to 6 months, causing this area to be frequently isolated, seriously affecting the economy and security. Faced with that urgency, the Indian government invested nearly $1 billion for the construction of a tunnel straight through the Himalayas. Once completed, travel time will be reduced from 3 hours to just 20 minutes, while also improving safety and ensuring year-round connectivity. Although the benefits are huge, the risks that come with it are also not small. Please note that we are talking about construction at an altitude of nearly 12,000 feet above sea level in extremely harsh weather, with frequent avalanches in the Himalayan mountains. Any mistake can lead to a tragedy. On November 12, 2023, during the construction of a highway in Uttarakhand near the Himalayas, India, a tunnel collapse occurred, leaving 41 workers trapped. Following that, in April 2025, at the Rishikesh-Karnaprayag rail project, also in Uttarakhand, engineers faced a life-and-death situation when a massive underground water pocket suddenly burst into the tunnel face. This serious incident once again reminded the world that the Himalayas have never been an opponent easily defeated. In contrast, the 14-kilometer Zojila Tunnel has not had any unfortunate incidents until now. This is related to the fact that engineers chose the NATM method, New Austrian Tunneling Method, with a flexible approach based on actual conditions, especially for areas with weak rock and complex geology like the Himalayas. So how did they do it? Please follow the video for more details. Don't forget to press like and share to give us more motivation to make more great videos. The process begins with a detailed geological survey before construction, as required by the National Highways and Infrastructure Development Corporation. The survey was conducted along the entire main tunnel route of about 14.15 kilometers from the two portals, Baltal, the Kashmir side, and Minamarg, the Ladakh side. The survey process includes determining rock mass condition, fracture levels, groundwater veins, and especially the specific geological conditions of the Himalayan region, where there are many easily fractured metamorphic rocks. After surveying and gathering data, engineers hold meetings to create the design as well as choose the technology. You might associate it with the image of a TBM mobile superfactory battling the super roof of the world, the Himalayas. Unfortunately, we cannot watch this classic battle yet, because surveys show that the specific geology in the Himalayan mountains consists of non-homogeneous rock layers, leading to being extremely easy to fracture. That is also the reason for consecutive tunnel collapses during construction in this dangerous mountain range. Additionally, assembling a machine over 100 meters long in a precarious place like Zojila Pass is extremely expensive and risky. Therefore, the optimal digging method is drill and blast and applying NATM, New Austrian Tunneling Method, to handle changing geology. Because of the harsh conditions of both terrain and weather, the first step in implementing the project is building accommodation and machinery storage. Workers' accommodation is built with high insulation, prefabricated structures, accompanied by heating systems. Material yards and machine stations are also built sturdily to ensure the best preservation. Simultaneously, independent power stations are installed to provide a stable power supply for the entire site, as the high-altitude local power grid is not reliable enough for a large project operating 24/7 like this. After completion, workers proceed with access excavation. At each tunnel end, they will build a portal and an access road at national highway scale. Because the tunnel length is up to 14,000 meters, workers need to build 3 vertical shafts up to 500 meters high along the tunnel for ventilation. The Zojila area is snow-covered for many months of the year, especially the Baltal side, so construction must be seasonally adjusted. This is why the project is designed as an all-weather tunnel. Next is the main construction process, starting with drill and blast in short cycles, round by round. The machine will drill holes to install explosives like this. The explosives used are emulsion explosive and ANFO because of their water resistance and effective explosion in wet conditions. After the explosion, muck-out work is carried out. Rock fragments are scooped onto trucks and transported out. A portion of selected rock is crushed to be reused as construction material for the internal structures of the tunnel. Lattice girders or steel ribs are installed immediately after excavation, with a spacing of 0.45 to 0.9 meters. These steel frames stabilize the shape of the tunnel cross-section and create a preliminary load-bearing frame. Then shotcrete is directly applied by workers onto the tunnel surface to serve as primary support. This layer has a thickness of about 200 to 300 millimeters, aiming to increase adhesion and disperse cracks, helping to limit falling debris and activate the load-bearing capacity of the surrounding soil and rock according to NATM principles. Next is the rock bolting work. Self-drilling anchors, SDA, with a diameter of about 32 millimeters and a length of 3 to 4 meters, are arranged alternately along the tunnel arch to sew the shotcrete layer to the natural rock. After drilling and installation, grout is pumped in by workers to fill the cracks. When the grout sets, bolts are tightened with bearing plates to ensure the anchoring force as designed. While engineers continue reinforcing the structure with steel, electricians proceed with installing the electrical system within the tunnel body. Due to the lack of oxygen at high altitudes, the duct ventilation system continuously pumps air into the tunnel, allowing workers to work continuously for 12 hours per day. Simultaneously, water supply pipes are installed to cool heavy machinery operating for long periods. The entire cycle above is repeated for each small excavation segment. Every day, the tunnel is excavated about 3 meters deeper through a cycle of drilling holes, placing explosives, and breaking the rock mass. The number might not sound impressive, but don't forget, this is the Himalayas. The NATM process, combined with drill and blast above, is always adjusted according to deformation monitoring and soil/rock classification, and does not fix a specific parameter, but depends on each geological layer. Therefore, monitoring deformation and geological observation within the tunnel is very important. This is also a factor that helps avoid unfortunate accidents that could occur. The measured data is used to adjust anchor density, adjust temporary reinforcement layers, and ensure structural stability throughout the excavation process. There is a specific obstacle from the terrain here. Melting snow from nearby glaciers causes water to continuously leak into the tunnel. To handle this, open drainage systems and multi-layered water pipes are installed along the tunnel axis to collect seepage water and distribute it outward, aiming to prevent water from pooling and exerting pressure on the tunnel face or initial support work. Simultaneously, a waterproofing system with an approximately 2 millimeters thick PVC membrane is installed behind the shotcrete or lining layer to prevent water from entering the concrete structure and prevent reinforcement corrosion, with a total waterproofing area of up to approximately 200,000 square meters along the entire route. Water is collected through porous/drainage pipes, leading to a drainage ditch system along the tunnel bottom, and is continuously pumped out by specialized pumps to ensure it doesn't affect construction or safe operation. By late 2025, the project reached about 60% physical progress. More than 12 kilometers out of a total of approximately 14 kilometers has been excavated but not yet completed, with all the structures and internal mechanical, electrical, technical systems. But this project is one of the exemplary works applying NATM in extreme Himalayan conditions, where there is heavily fractured rock, melting snow water, and high groundwater pressure. The tunnel is excavated by drill and blast in short steps, combined with continuous deformation monitoring, allowing for adjustments of shotcrete, rock bolts, and steel arches according to the actual reaction of the rock mass. This approach helps control long-term stability at an altitude of nearly 12,000 feet, which is very rare for a 14-kilometer-long road tunnel. What project do you want to know about next? Let us know in the comments.